Hi Year 13, this video is going to go through some hints and tips for the second integration assignment. It's 5 questions long this time and the usual total is out of 50. So we'll go through these one at a time. If you want to make some notes and annotations, please do, as you might find some of this helpful, hopefully. So the first question here has got a function y equals x sine squared x. It's shown in the picture. We want the area bounded by these lines here, where x is pi over 2 up to pi. And you want to do some definite integration there to get that area. Now, looking at the form of the function that you've got, it looks like this is a product of 2 different functions. And by different, I mean functions that are in different families. So x is a polynomial function, and sine squared is obviously a trig function. So it suggests here that you probably want to use integration by parts, because that deals with products of that form. Okay, and then that's 7 marks. Go through this quite carefully. It's going to be quite difficult to integrate sine squared unless you know the trick. So take a look through your notes if you're not sure how to do that. But yeah, 7 marks to get that area there. And keep it in exact form, please, as well, because that's normally what a question is going to want you to do. Okay, question 2. New function this time, you've got the curve y equals a half x cubed times the square root of 4 minus x squared. So clearly this is going to lead you into a trapezium rule question. You can see that from the table that you've got. You want the y value for x equaling 1.5. That's easy enough for 1 mark. And then given that I is this integral here, that's going to give this area between 0 and 2. Just double check that this part here does exactly match what's up here, and it does. There's no difference there. So then you want to use the trapezium rule with 4 equal strips. That's the same as saying 4 trapezia, but note that's going to give you 5 what we call ordinates there. It's going to give you 5 x values because your 4 trapezia will give you 5 x coordinates like that, okay? All right, so for 3 marks, use the trapezium rule. It's in the formula book, which I'm going to attach to you as well. Otherwise, you'll have it in your class notes. And you want your answer as well to 4 significant figures. Make sure you do that as well, please. Part C, it wants you to actually carry out the integral and get an exact value of this area. It's giving you the method to use, which is an appropriate substitution. I'm hoping by now you can look at that and decide a sensible U substitution if you use for that. And then your answer wants to be a rational number in its simplest form, so a fraction basically. And that's 6 marks to do that. And then for 1 mark, part D, suggest one way in which your estimates using a trapezium rule could be improved. So you've got to think about how modifying your trapezium rule is going to give you a more precise answer for the integral, and I'll leave it to you to say what that is. All right, moving on to question 3. You've got a rational function here where x is not a quarter and it's also not 3 over 2, minus 3 over 2. That's going to stop you from putting 0 into these brackets. However, when you break into partial fractions here, you're going to be at some point clearing denominators. So at the point where you want to be subbing in values of x, just because it says this up here doesn't mean that you can't use it to work out your partial fractions, your numerators. Okay, so I'll give you that much. Don't be put off by the fact that that's telling you not to use a quarter and minus 3 over 2. You can, once you've got rid of these denominators that causes the problem there. And then once you've done that, we're now integrating these, and it wants the exact value of the integral from minus 1 to 0 of f of x dx. Bear in mind, just because you've got 0 here, that doesn't mean that your function is going to be 0 when you plug the values in. So I'm going to say that capital F of 0 equals 0, right? Most of the time, in year 1 in particular, sticking in 0 into an integrated function is going to give you 0, but it doesn't necessarily mean that, so do check that, please. And that's 5 marks to get that integral there. Okay, number 4, this is going to be the first of 2 differential equations questions. So the value of a computer, which is v, decreases over time, which is t given in years. The rate of decrease, remember that word rate, and discuss what that means. Decrease as well, that tells you something to do with what's going on in your differential equation. is proportional to the remaining value. Okay, we've seen plenty of examples where that's the case, where you've got the rate being proportional to the function itself. Given that the initial value of the computer is v0, show that v equals v0 times e to the minus kt. Okay, so that's to do with setting up your differential equation and doing something with this initial part as well. Okay, now that's 4 marks there. After 10 years, the value of the computer is a fifth of v0. So quite clear what to do there. It's going to be time being equaling 10 years. Make sure that your units match the units that's given for t, and it does. So exact value of k as well, it wants that as some exact value. And I can tell you that the form of your answer is going to be k equals a times the natural log of b. That's what it's asking you to get to at the end, where a and b they can both be positive, and they're also rational numbers as well. Okay, so that's the form of the answer, if you can get it to look like that. And then for part C, how old is the computer when its value is only 5% of its original value? I wouldn't use 5% in your equation. I'd turn that into something more manageable to use as 5%. And then it's asking for how old, so that's obviously going to be working out time. Use your value of k as well in your answer for part C, so you can get to just the value of t there. And it also wants the answer to 3 sig fig. Make sure you do that too. Right, 3 marks to work that out, and that finishes off question 4. Okay, moving on to the final question, question 5. So you've got a large cylindrical tank with radius 40. Now, I can't see a diagram for this, so I definitely draw a picture to help you write down at least some of the information you're going to need to work out this question. Okay, pretty important that you want to be doing that quite early on. Right, radius 40 meters for your cylinder. Water flows in at a rate of 4,000 pi meters cubed per minute. At time t, the depth of water in the tank is h. Water leaves the bottom of the tank through another pipe at a rate of 50 pi h meters cubed per minute. So you've got these two rates, one of which is flowing in and the other which is flowing out. And then show that this differential equation here is true after t minutes. So bear in mind what we discussed when we looked at kind of rates of flow of a liquid in and out of a container here. You've got the rate overall is the rate in, which is going to be positive because it's going in, minus the rate out. So that's going to be the kind of bare bones structure of your differential equation. You've just got to make sure everything goes in the right place, and you can end up at what it's got here as your final answer. That's for 6 marks. Okay, then you've got some extra information here. You've got an initial condition, t equals 0, h is 50. Find the exact value of t. Important that you have it exact when h is 60. So looking at this, you want to try and solve it using the methods we've covered in the lesson. And I can tell you that this is in separable form. Okay, and you've got to think about what needs to come over to each side of the equal sign in order to solve that in the most efficient way possible. Okay, 6 marks to solve this differential equation and work out this value of t. That's 6 marks there and brings your total to 50. So if you can start this in today's lesson, and then I'll be looking for that to be submitted sometime next week. Take a look on Show My Homework for the exact times there. All right, thanks, year 11. Not even year 11, actually, year 13. I'll see you soon.